You see them everywhere, right? These giant steel cylinders just sitting there. But what's really going on inside? Well, they're pretty much the unsung heroes of our entire energy system. So in this explainer, we're going to pull back the curtain on petroleum storage tanks. We'll get into the incredible engineering, the really clever designs, and of course, the critical safety rules that keep them and all of us safe.
All right, so here's what we've got lined up. First, we'll talk about just how massive these things are. Then we'll get into why you can't just use one type of tank for everything. After that, we're going to take a look inside, at the anatomy of a tank. We'll also cover how they get their high-tech checkups, and we'll wrap up with the super important human side of keeping everything running safely.
Okay, first up, the giants of the industry. Let's just try to get our heads around their sheer scale and what they're actually for. You can think of these tanks as like the giant buffer zones for the whole world's energy supply. They're the critical link between getting oil out of the ground, turning it into fuel, and getting it to you. Seriously, without them, the whole system would just stop.
Yeah, just look at that. A picture like this really brings home the kind of scale we're dealing with, right? These places, these tank farms, they've been a cornerstone of the oil and gas industry pretty much since day one. And they're holding, well, everything, from the raw crude oil literally just pulled from the ground all the way to the finished gasoline that's just waiting to be shipped out to your local station.
But their job is way more than just holding stuff. It's way more complex. Think of them as the pantry for a refinery, storing all the raw ingredients. They're also the warehouse for all the finished products. They even act like giant mixing bowls where different fuel blends are created. And they're also settling ponds, letting all the gunk, like water and dirt, sink to the bottom so it can be drained off. Every single one of these functions is a totally critical step.
And this quote, yeah, it really cuts right to the chase, doesn't it? The stakes here are absolutely massive. A single tank failure isn't just a little leak. It's a potential catastrophe. We're talking danger to people, a disaster for the environment, and a huge, huge problem for the business. That's why making sure these things are rock solid isn't just a good idea. It's completely non-negotiable.
So how in the world do you design something this big to be safe? Well, it all boils down to a classic engineering principle. Form follows function. The kind of tank you build is 100% determined by what you're going to put inside it. Specifically, how easily that product wants to turn into a gas. Engineers have a couple of words for this: volatility and vapor pressure. And that basic idea leads to two main families of tanks. On one hand, you've got your atmospheric tanks. These are for the chill liquids like kerosene that are perfectly happy staying liquid at everyday temperatures. But then on the other hand, you have pressurized tanks. These are for the really volatile stuff like propane, the things you have to keep under some serious pressure just to stop them from basically boiling away into a gas instantly.
And here you can see that whole idea in action, plain as day. Over on the left, that's a pretty simple fixed dome roof tank, good for less volatile stuff. But the one on the right, now that is a seriously clever design. It's called an external floating roof. The roof literally floats on top of the liquid. It's a brilliant bit of engineering, really, because it gets rid of all that empty space at the top where flammable vapors could build up. That prevents emissions, which saves money, and more importantly, is way, way safer. Okay, this table breaks it all down perfectly. See? For something not very volatile, like kerosene, you use a simple fixed roof tank. As you move up the scale to things like crude oil or gasoline, you switch to a floating roof to handle those vapors. And then, for the really high-pressure stuff, LPG, butane, you need these super strong, specialized tanks. They're often called bullets because of their shape, and they are built to handle all that pressure.
All right, so I think we get the why behind the different designs. Now let's kind of pop the hood and take a look at the what. We're going to break down the anatomy of a storage tank, from its basic skeleton all the way to the little gadgets that are essential for keeping it safe.
So if you look at a basic fixed roof tank, its anatomy is actually pretty straightforward. You've got the big cylindrical wall, that's the shell. You've got a fixed roof on top. Now on the really big tanks, that roof needs some support, so it'll have columns inside. And then you have these things called manways, which are basically just access hatches so people can get in and out for inspections and work. Now the floating roof design. This is where the engineering starts to get a little more complex. Since the roof actually moves up and down with the liquid, you need a clever way to get onto it, so they use a rolling ladder. But the absolute key to this entire design, the real linchpin, is the rim seal. It's this flexible barrier that fills the gap between the moving roof and the tank wall. If that seal isn't perfect, the whole point of having a floating roof is just gone.
Tanks have a ton of different fittings and valves, but this one right here, this is the true unsung hero of any fixed roof tank. It's the pressure vacuum safety valve, sometimes called a double breather. And honestly, the best way to think about it is like the tank's lungs. When you pump liquid in or out, or even when the sun just heats up the tank, the pressure inside changes. The tank needs to breathe, and this little valve lets it do just that. It inhales and exhales, preventing it from getting crushed by a vacuum or blowing its top from too much pressure. It's such a small part doing a massive, massive job.
So, okay, we've got these colossal containers full of potentially hazardous stuff. How do you give them a health check? I mean, really, how do you guarantee they're going to stay strong and not leak? Not just for next year, but for decades.
Well, this is where some really cool technology comes into play. The days of just walking around and looking at it are long gone. Today, operators have this whole toolbox of high-tech gear. I'm talking about ultrasonic robots that literally crawl up and down the walls, measuring the steel thickness. They use drones to fly around inside to check out the roof, so nobody has to go in. And they use 3D laser scanners to build these incredibly precise digital models to spot even the tiniest bulge or dent.
And the inspection checklist? It's exhaustive. I mean, they're not just looking for the obvious stuff. They check the foundation to see if it's settled even a little bit, because that can put huge stress on the whole structure. They scan every single inch of the shell for corrosion. That's the #1 enemy of a tank. They even check the lightning protection. It's a complete top-to-bottom, systematic hunt for any tiny flaw before it has a chance to become a big problem.
And that brings us to our last section, which is maybe the most critical of all, the human element. Because all the robots and scanners in the world can't replace the need for actual people to do maintenance and repairs. But think about it. Sending someone inside a container that used to be full of flammable liquid, it's one of the most dangerous jobs out there. And that's exactly why the safety rules are so incredibly strict.
Before anyone, and I mean anyone, sets foot inside that tank, it has to be made gas-free. This is the absolute 100% non-negotiable first step. The entire goal is to get every last bit of flammable and toxic vapor out of there and replace it with clean, breathable air. You're basically taking a deadly confined space and transforming it into a safe place to work.
And you better believe that process is meticulously controlled. Step 1, you empty the tank completely and isolate it. That means physically disconnecting all the pipes. No mistakes. Step 2, you ventilate it to get all the bad air out. And a key point here, you never use pure oxygen because that would be a massive fire hazard. Then, the air inside is tested over and over again, and only when those tests come back clean, proving it's safe, is a permit to work issued. Only then can the real cleaning start.
But even after all of that, there are still hidden dangers lurking. Get this, the high-pressure water they use for cleaning can actually build up static electricity. And some types of rust deposits, the stuff called pyrophoric iron sulfide, can literally just burst into flame all by themselves when they dry out and hit the air. It's crazy. That's why they take every single precaution you can imagine, like using special tools that don't create sparks and making sure absolutely everything is grounded.
So, all of this leaves us with a pretty fascinating question when you think about the future. As our inspection tools get smarter and smarter with things like AI and robotics, and as we learn more about the materials themselves, how is that health check for our most critical infrastructure going to change? How do we make sure these silent giants stay safe and sound in a world that's constantly evolving?